recording. Okay. So, welcome to this week's seminar. It will be about instrumentation, specifically compiler instrumentation, as a way for performing dynamic analysis of programs. So, just to start some goals for today. So we will see how dynamic analysis is performed, what it is about, and specifically we'll be talking about both binary and compiler-based instrumentation. And then, as I would say, the main point for this seminar session will be how to use CSI, which is an instrumentation framework provided by the Tapir compiler, presented by PB last week. So let's start with some motivation. So imagine the following scenario. You're working on performance engineering. You're well known to be good at finding performance problems. So a colleague or a friend comes up to you and says, I have this code which doesn't really perform well. And I would like you to have a look at it to see if you can, for example, find if memory is not handled correctly or something like that. And you will say, okay, sure. But then your friend or colleague warns you and says, be careful, this is legacy code. So it may not be the best. You have to know what you're getting into. And you say, sure, I work with legacy code all the time. So you go up and ask him, so show me the code. And he shows you something like this. And you're like, okay, so maybe just looking at the code is not enough to see where the problems are. So this is actually an extreme example. This is actually from the International Contest for Obfuscated Code. This is a winning entry. And just to see what we are talking about, I'll show you. Let me show you what this code does. This is actually, let's see if we can stop the presentation. Yeah, so let's go. This is actually working code. And it's a simulation of a constellation configuration. It's very hard to see, unfortunately, on this screen. But it's actually simulating one of the constellations. So there are codes like this. I will even say the legacy code for scientific computation is even worse than this. But your mileage may vary. So now that you've seen, this is one of the few, one of the actually many motivations why you don't always rely on skill, to look at source code. Sometimes you want something more like dynamic analysis. And let's see if I can get it. Yeah. So what is dynamic analysis? It's a very broad topic, and it can be summarized as basically a way to collect information about a single or multiple specific executions of a program. So this differs from static analysis, as Mike presented a couple of weeks ago, in the way that this is not something that tells you something defined about the program in every aspect, but some specific execution, maybe the one you most care about, like the workload that you know the program will undergo. So this kind of analysis is able to answer questions such as how many function calls does the program make, as I say, in this execution, how many memory accesses result in a cache miss, this is good for performance, what's the function that takes most time, so this is profiling, and so on. There are many scenarios, many kind of information that you can get from dynamic analysis. So the main use cases are actually profiling. So this is a screenshot from Intel V2, which is a profiler by Intel. But then we have Linux perf, cache client, for example, as open source alternatives. Dynamic analysis is used for debugging, for example, Valgrind, which main, let's say, objective is to investigate memory leaks, but it also does other stuff. And then dynamic analysis is even used for optimization. For example, compilers have this concept of profile-guided optimizations, where the compiler will instrument part of the code to add like statistic collection, and then it will use those statistics to, for example, optimize the code in a ways suited for a specific execution. For example, we'll devirtualize function calls, inline functions that are hot, and so on. So what are the techniques, the main techniques for performing dynamic analysis? Well, most of them rely on instrumentation, which is the augmentation of code in order to insert, for example, arbitrary information collection or some specific logic that you want to run on the execution of the program. So there are many kinds of instrumentation. There is source to source. So for example, you give it a C file, a C source code file. It will insert some additional syntax, some additional code that will basically be compiled then, and the additional code that is added to the source is what will be the instrumentation. Then we have binary instrumentation, which can be both static and dynamic. Static binary instrumentation is when you have a binary that is already been compiled. You feed it to a instrumenter that is able to modify the code from the binary and create another binary, which is the same but with the instrumentation. And then we have dynamic instrumentation, dynamic binary instrumentation, where the binary is run almost as normal, but usually there is a virtual machine on top of that. And before executing an instruction, the virtual machine can insert arbitrary instrumentation code. This is, for example, what Valgrind does. There are some more techniques. So another very popular one is compiler-based instrumentation, where the instrumentation code is added at the IAO level most of the times. And so the compiler just goes through the code, but before compiling it, it adds some more arbitrary code for instrumentation, and then the pipeline is as normal. And then there is I would say, less popular alternative, but I've seen it become more, I've seen more applications of it lately. So there's hardware instrumentation, where, for example, a component in the hardware is responsible for snooping the CPU, looking like what instructions are executed or leaving the memory bus, and it executes specific actions. It usually is not able to perform arbitrary instrumentation. But I would say that, for example, hardware counters are an example of this, a very small example where the CPU itself keeps track of what it's doing and reports it. So with all these techniques, it may be difficult to understand what to use in your case. And to be very clear, there is no silver bullet to dynamic analysis. I would say the most popular one is binary instrumentation, but as we will see, it has some drawbacks. And in some cases, those drawbacks are a showstopper, and you need to move to something else. And so what are some aspects that we take into consideration when deciding which technique to use? So one is definitely performance. If instrumenting your code makes it go 100 times slower, it may depend on your use case. But if you're using a real workload, it may not even finish before getting the information you need. So performance is definitely a huge point to take into consideration. Then there's flexibility. There are some tools that let you perform, I would say, specific instrumentation like profiler tools. So you use them and you get one kind of information. It's very difficult to change those to maybe meet your needs. Like if your profiler doesn't give you the information you need, you have to find another way. So you have to see how flexible the tool you're using is. Then there is ease of use. I would say if you, for example, use a tool like Intel VTune, it's very easy to use. It's binary instrumentation. You give it the binary that you produce as normal. It gives you some information, and that's it. If, for example, you want to use hardware instrumentation, then you have to find something to use the hardware counters. For compiler instrumentation, you have to modify the compiler and so on. And then an important point is dependencies. For example, binary instrumentation tools work by basically understanding what a binary does. And the binary is highly machine dependent because it's binary code for that architecture. For example, if you want to use vTune, you will have a great time on x86, but what if you have a smaller architecture that is not supported? It's just not going to work. Where, for example, compile instrumentation can be architecture independent. So this is a thing to take into consideration. Now, I talk a lot about binary and compiler instrumentation, so this is what I will be focusing on. So let's take a closer look at how they differ and the main points of commonality and differences, basically. So binary instrumentation, as I said, is very architecture dependent, but it's language independent. It only cares about the binary. It doesn't care about how you got that binary. Compiler instrumentation, on the other hand, is both language and architecture independent, as long as the compiler instrumentation is implemented at the IR level. So the IR level is the good abstraction that lets you not care about either the front end or the back end. So, for example, as long as you get IR, as long as your compiler is able to have a front end for something, it will go to IR, and then you can instrument it at that point. Binary instrumentation is very, I would say it's very easy to incur performance degradation with binary instrumentation. Actually, there are many, I would say, for binary instrumentation frameworks, it's a huge concern for them to provide you a way to write instrumentation code that performs well. If, like naive instrumentation, for example, stopping at every instruction and doing something, it's very expensive because the CPU will have to basically do more than double the work for every instruction. So that's going to cost. And binary instrumentation don't have I would say, an organic view of what is going on in your program. So achieving good performance is a challenge. On the other hand, compiler instrumentation can achieve good performance without you caring about performance. If you add some code at the IR level, the compiler will optimize it like it's normal code. It will not know that it's some instrumentation. So it will basically give you some optimizations for free. For example, inlining. In terms of binary instrumentation, like I would say ease of use, it's easy to access as long as your framework supports it. There are many frameworks, they're well known. Some examples are, well, Valgrind, Dynamo Rio, Intel Pin, and those are very good if you, for example, as I said, you're on x86, which is I would say, the main target for them. They have support for like ARM and other architectures, but once, for example, for embedded devices, it may be a challenge. If they don't work, you're out of luck. For compiler instrumentation, well, most compilers don't give you a way to access instrumentation as easy as a binary instrumentation does. So it may be very hard to come up with something that you are comfortable with when using compiler instrumentation. So it's definitely not as user-friendly as binary. For binary instrumentation, another pro is that you don't need the source code. So this is a bit different from language independence. This basically means you don't need the source code at all. So if you have a legacy binary, which unfortunately there are quite a few of those, both in industry and in academia, you can do binary instrumentation pretty easily because it's just a binary like any else. For compiler instrumentation, you need some, I would say, source, some origin for that binary, whether it is source code or IR. If the compiler does instrumentation on the IR level, as long as you have the IR, but maybe not necessarily the source code, that's good enough. So these are the main differences, I would say, from binary and compiler instrumentation. Binary is very popular. Compiler has its users, but it's way more difficult to come across because you need some compiler expertise. But what if you don't need compiler expertise? That's why CSI, that stands for Comprehensive Static Instrumentation, was initially devised for. The original work was done with TB, Angelina, Charles, and other people that you see. This is a reference, and there is a link to the paper in the last slide. So what is CSI? CSI is an instrumentation framework that has been embedded into LLVM, specifically the Tapir compiler, that makes it easy to write dynamic analysis. Like, I would say, if you look at the workflow for binary instrumentation, this is the ideal corresponding workflow, but for compiler instrumentation. So the focus of the work was that the compiler, the tool writer didn't need to know what a compiler was doing. It didn't even need to know what a compiler is in general to write some analysis for your program. So it provides facilities to easily write tools, and also some additional features like tables to access debug information at runtime, and a flat ID space for performance, which we'll see later, is a huge feature of CSI. So as you can imagine, CSI inserts instrumentation at the AI level, so it's architectural language independent for the most part. It does have a runtime, but as long as the runtime can be compiled for your architecture, and the runtime is just a single C program, C level would be a library, so it's usually not a concern. So how it works at a very high level is the user provides some instrumentation for which you want your target program to be instrumented with, and then the compiler and CSI internally will just add this instrumentation at specific points. For example, function entry exit. So we see here an except for the CSI interface. You have a function called CSI function entry. You insert your code here, for example, I don't know, you add a counter, so you count so many times a function was entered, or you print the function name. What CSI will do is take that code, which you write in your language of choice, mostly C or C++, and then insert it while compiling your target program. So I said function entry exit, then we have support for example, before and after every memory access, or memory load, memory store, before and after a function call, for example, to our external library, even basic block level, before and after allocations if you want to keep track of your memory consumption. And there are many more, and we are adding more for specific use cases. And we want it to be as flexible as possible in terms of what you can do and how specific you can be in what you want to instrument. So if you want to instrument only functions, you're good. Or if you want to instrument only memory access, you're also good. And if you want to instrument everything, you can do that. So I already said, I already gave some explanation why we are doing this at the AI level. One thing is architectural language independence, but there is another argument for it, which is probably even more important. So one goal for CSI is that the tool writer shouldn't have to worry of the performance of his instrumentation just because of how instrumentation is done. You should just worry about the performance of your instrumentation code as normal code. Like you're using too much memory, you're wasting CPU. You shouldn't worry about, oh, this is slow because I'm doing compiler instrumentation. No, this is slow because the compiler is doing something. So having the compiler insert instrumentation at the IR level makes it possible, as I said, to use compiler optimization, the same one that you use for normal code, and for example, inline instrumentation code, optimize away instrumentation code that is not needed, coalesce operation, and so on. Stuff that you cannot do with binary instrumentation, or possibly with any kind of instrumentation, because you don't have a view of the normal program, and you cannot at that point change the behavior of the program. And a research question that is important here is Are further optimizations specifically for instrumentation code possible? So can we change the compiler to even perform more optimizations knowing you're adding instrumentation code? As you can imagine, most analysis code does not interfere with the normal program. You just do some analysis on top, you count, you perform statistics, you don't change the behavior of the program most of the times. So there are when you are adding instrumentation code, you're basically adding code that doesn't touch the other code. So can the compiler make some, can infer properties about this and basically make it even faster? So this is a question that needs answer, and it has not been researched a lot yet. So I talked about some features that CSI has that other frameworks don't have. So for example, the flat ID space. So what's the flat ID space? Basically, the way CSI works is that for every instrumentation point, be it a function call, a memory access, anything you can instrument gets an ID. And that is guaranteed to be unique. And no matter how much code you have, all the IDs are contiguous. So for example, if you have 5 functions, you will have five IDs in an array. And having this in a simple array and like a guarantee that all these IDs are contiguous means you can keep track of statistics much better. You can use arrays instead of hash tables or trees or whatever is your favorite data structure. You can use linearity as a way to gain performance. And makes it, these features make it easy to perform queries such as which basic blocks have not been executed. So suppose in any other framework, you get an ID for a basic block. For example, you get a hash, or you have to devise your own ID based like on the instruction inside. You keep a hash table, say, which maps ID basic blocks to how many times they've been executed. Now you get at the end of the program and you want to know which basic blocks have I not executed, but you don't know which basic blocks have not been executed because the ID space is a hash, and you only know the ones you've gone through. So in this case, otherwise, if you have a flat ID, you can just go through the array, see which ones you never hit, and you can just do a simple difference and you get your answer, which is way, like you can do, obviously there are ways to do it in other frameworks. It's just more intricate and doesn't yield the same performance. So along with this flat ID space, we also have the concept of front-end tables. So for each instrumentation point, CSI also gives you a way to collect some, I would say, debug information. For example, for functions, you get the function name. So we say here we have 5 functions in this program. And when you see, oh, function number 3 has been executed, you can ask CSI, what is function number 3? And it says, it's function called run experiment. Or what's function number 5? And it tells you, oh, this is function f open. This is usually good for, like at the end of the execution, you want to report information. This is what you use to actually make it human readable. And same for memory stores. For example, this program, there are 4 stores, and it tells you where they are. For example, main at line 45. So this actually has information about the source code. If you have debug information, that's very useful. For example, for debugging, performance profiling, and so on. So we have one table for each type of instrumentation point, so function, memory load, memory store, and we have one for each thing. And all of them have their own ID starting with 0 and until they contain all the things for the entire program. CSI being at the compiler level, it's actually easy to write tools that are independent of whatever you're using. So as I said, architectural language independence is a huge thing. And we demonstrated it by using CSI in many different contexts with little, I would say, adaptation. It's very flexible, and you don't need to change much. As long as the language you use is based on LLVM, you can use CSI. So we have C and C++ programs, Silk programs that use Tapir. We even have some languages that rely on a JIT. And as long as the JIT is implemented with LLVM, adding CSI is a matter of a couple of lines. So we did some debugging of TensorFlow. With the XLA compiler uses LLVM. We have done some profiling for Julia and Python, which is still in the early stages. There are some projects that basically JIT compile Python to native code. Numba is one of those, and it uses LLVM. Now, CSI sounds great, but there are some drawbacks that people need to take into consideration, and those mainly stem from it being compiler-based. So one obvious thing is you have longer compilation times. Adding this instrumentation takes time. It's just another compiler pass, and the compiler can be slow, especially if you want your instrumentation code to be as efficient as possible. You want to rerun some optimizations after the instrumentation code is added. Rerunning optimizations is not a problem for the compiler. It actually does that already. It reruns optimizations over and over in different, ways. But this takes time, and if you're adding a password that needs more optimizations, well, you're going to see that in your compilation times. Another problem is there's a slow feedback loop for tool writers. So you write your tool, you test it on your program, and then you realize your tool has some problem, you don't get the information you need, or it has a bug or whatever. Now you change your tool, you fix it, you get what you want, but then you have to recompile the entire program in order to see how the tool behaves now. This is partially mitigated by testing your tool on a small program, and then when your tool is ready, you move to your large code base that you want to analyze. This is not always possible because a bug can happen only in that code base and not when you're testing, but it's something to take into consideration. For binary instrumentation, you don't have to do that. And of course, it requires source code or at least IR in order to function at all. Otherwise, if you just have a binary, some ways are, well, binary instrumentation, or if you're really desperate, you can decompile it to whatever using the compiler. You don't need to read it. You can just feed it back into the compiler and use CSI. We didn't try this. It's something that we hope is possible. But it definitely depends on how good the compiler is. So let's see at an actual example of how we use CSI. So during the last semester, we worked on a tool that is able to infer properties about the memory usage of a Silk program. So CSI can, since it's embedded into the Tapir compiler, can easily instrument Tapir constructs. So for example, you can say instrument, add this code before a spawn, add this code after a sync, or this is a parallel for loop, so you can add code to perform operations at that point. So it's very easy to write tools that infer properties about the parallel structure of the program, because you can get the parallel structure by instrumenting those points, for example, where the program branches. So the example that I wanted to give and what we worked on is basically an answer to this question. If I know how much memory this program uses when run with one processor, what's the maximum amount of memory it can possibly need with n processors? The easy answer could be n times the memory used by one processor. This is most of the times not accurate or not correct at all. So this kind of, I would say, this kind of information, you need to actually run an analysis on your program. And there are, this was work done by William Kussmaul and TB Shardle, and Tim Kaller and me. And there are algorithms to determine the answer to this question. So we actually built this tool, and we are on a case study. So this tool called SilkMem has been run on a program that performs image alignment on a set of images, medical scans of a mouse brain. This is very like performance-sensitive code. So the originally worked by Tim Kaller, and we actually found an interesting behavior. So we found that the program ends up allocating more memory when more processors are used. And while this is not surprising in itself, because there are many programs that do that, it was certainly unexpected to Tim that who wrote the code, because he carefully engineered it to make sure that no matter the parallelism, the actual like dynamic allocations should be the same, but they weren't. In our case, it wasn't that big of a deal. It was, I think, a couple of 100 megabytes per additional processors. But if you're running it with 128 processors, you're going to use a couple of gigabytes more. And that was bad, and well, that was unexpected. So we ultimately found out it was due to OpenCV, the computer vision library used by the program, that had some behavior that was not known and was not very clear. So we were able, using SilkMem, to debug this and find the root cause. How does SilkMem perform in terms of overhead? Well, it actually performs pretty well. So we run this, we run the tool on a set of benchmarks taken from the SilkMem, the Silk suite of benchmarks that is available on GitHub. And well, there are many parameters, but if you run the last column is about the approximation algorithm, the one you want to use to get like a quick glance of how memory is used by your program. And even with the worst case, which is Cholesky, we only get less than 5 times overhead over the serial execution of the program. But most of the actual, I would say, average programs, you don't go more than twice or even 50%. I think the image alignment program where we tested, where we did the case study, had a lower than 20% overhead. So that was really easy to determine. Yeah. And additionally, so since it's based on memory, we also instrument memory allocations. And basically, that and function entry and exit for some additional bookkeeping and like debug information. As a bonus, the good thing about Tapir and like serious parallel programs is that they have a very defined structure to it, a parallel structure, and you can actually visualize it. So SilkMem actually is able to present this visualization to you after you run the program. So this is an execution of fib6 using Silk. And so red edges are spawns, and blue edges are continuations. So this is actually pretty good to add the visual information. And I want to show you how, like this is just fib6, but I want to show you something more intricate than this, more complicated. So let's see if I can. Okay, so let's do fib of 10, for example. If you visualize it, you can see the entire computation, and it's really useful to look at a glance what's going on in your program. Are you getting parallelism? Yes. Or some other information that may be difficult to see just by looking at the source, for example. And as an additional bonus, I also have a picture from the actual image alignment program. So a visualization how, let's say, intricate it turns out that the program behaves. So it's actually too big to be embedded into any like PDF, image, or whatever. So this is just a small window of the entire program. Let's see, it doesn't crash. Okay, yeah, it's too big. So you can see how the structure of the program is just from looking at this. And this actually has more debug information. So if we zoom in, each node is actually telling you where it branched, or where it spawned. So this is in the function compute key points and matches, line 2740. So there is a lot of information that you can add, very easy to access. It just requires a couple of lines of CSI. So we talked a lot about dynamic analysis. Turns out that CSI is flexible enough for even more than just analysis. So recently, TB added some, let's say, capabilities to CSI that basically gives you more information about the control flow of the program. So you can keep track of variable allocation and then where it's used, by making these kind of correlations, made it possible this is joint work by Tim Carter and TB, to write a tool that performs auto-differentiation just based on the IR. So you have your C program, you feed it through the compiler to this special CSI tool, and then you run it, and basically performs auto-differentiation of arbitrary code. So that's pretty cool. It's still in the works, but even when comparing the performance of this, you will expect this to be quite expensive. But comparing the performance with state-of-the-art auto-differentiation libraries or frameworks, this actually doesn't perform as bad. It's sometimes it outperforms other things that you would expect to perform better. So it's pretty cool what you can do with CSI, and it only depends on how creative you get. So let's see what the workflow for actually writing a CSI tool is. Like, how do you get to write this analysis? It's actually pretty easy. So I'm going through some information now, but I will also show you it in how it works by showing you an example and compiling it. So you write the tool, whatever you want, that as long as it implements the CSI interface, which is provided by the Tapir compiler in the source. And so you implement your, for example, CSI function entry function, so that will be added to every function entry. You implement your on-memory load function that will run after every memory load, so on. So whatever you want to write. If you don't want to use a specific instrumentation point, like functions you don't care about, you just leave them empty. The compiler will know about it and will say, okay, this is empty, I don't even need to instrument, I don't need to do anything. So you basically write only what you need. Then you compile the tool both to a shared library and to LLVM IR. We will see why this is necessary, or why it's highly suggested. Then you identify the target program you want to instrument. For, let's say you just have a program of one source. It doesn't matter. You can have as many files you want. So program.cpp. You compile program.cpp with a special flag that tells you to use CSI. So you say, I want to use CSI, so fCSI. And then you give it the bitcode of the tool. I will show how this is used. Finally, you link the program with the CSI runtime, also provided by Tapir, and the CSI tool you just wrote. So in the end, you have your program, the CSI tool you just wrote, and the CSI runtime. And then you get an instrumented binary that you just run, and it will perform like the target program with the instrumentation. So before we dig into it, why we pass the tool's bitcode to the compiler? So CSI accepts this bitcode on the command line. And the bitcode is actually used for optimizations. It's not necessary. You can still get your behavior, but it's highly recommended because if the compiler has access to the instrumentation bitcode, it can look and say, oh, this, let's say this instrumentation is not used, so let's not put it at all. Or this is such a small instrumentation piece that, for example, you just add a counter, you will say, oh, this can be inlined. So you actually get huge performance boost just for that. If it's not able to do anything, like if you have an instrumentation function that is 100 lines and the compiler says this is not worth inlining, we just insert a call to the tools library. So that's why you need eventually to link with the tool library, because if it's not inlined, it needs a way to reach that code. So let's actually write a CSI tool. I have an example which I can share after the seminar. So let's go. Okay. So first, as I said, we have to write a tool. In this case, I prepared a tool that counts how deep you go in the stack, so how many nested function calls you do during an execution, and it also counts how let's say how many times any function is called. So let's look at the code. It's actually very simple. So can you read, or should let's... Yeah. So you include the CSI header provided by Tapir, and then you write your program like you will write any program. You just make sure you implement these functions. You can treat it like as a base class. You have to an abstract base class that you have to implement. So, for example, this function is called every time a basic block is entered. CSI BB entry. We don't want to do anything with basic blocks. We don't care. So we just leave it empty. Same for before store, after store. We don't care about memory access. Then we have, for example, CSI detach, CSI task. This is the Tapir instrumentation. A detach is a spawn. A task is a continuation or a spawn task. Before sync, after sync. This is also Tapir. Then we have before alloca, after alloca. So before a stack allocation and after a stack allocation. Before free, after free, or before malloc, after malloc, and so on. Then we have a special call. This function, CSI unit init, will be called once per every translation unit you instrument. So in the previous case, we have like program.cpp, it will be called once. And this function gives you information about how many things you're instrumenting. For example, it will tell you in this counts variable, it will tell you, oh, we are instrumenting, like this translation unit contains 5 functions, 10 basic blocks, 15 memory accesses, and so on. So this is a way to keep track of the, let's say, global state of the, as translation units are added, in the end, you get a global state of the entire program. So for example, here we are outputting how many functions are in the translation unit. So counts.numfunc. That's pretty easy, and all of these member variables are in the CSI header, which you can access and see what you need to, what kind of information you can get. And then we have something that we actually care about, so CSI function entry. This function is called every time a function is entered. So we have some variables to keep track of stuff. So we increment the stack depth because we are going in. We increment the number of calls. We just entered the function, so it was called. And then very easy to keep track of the maximum one just to report at the end. And then if we are like a verbose flag, we also output. We are entering the function, and instead of just using entering function 1, entering function 3, we use the front-end tables that I showed earlier to actually get the the name of the function. So we can say entering function main, entering function pow, entering function fopen. And we also report the current stack depth at that point. The other instrumentation point we care about is function exit. So at a function exit, we just decrease the stack depth because we are going up. And as again, if we are verbose, we say we are exiting the function, the name of the function, and the current stack depth has been decreased by 1. CSI init here is a special function that we call once at the beginning of the program. Before anything is executed, you can do some bookkeeping, whatever you want, like prepare variables and so on. In this case, it's a very common pattern in CSI tools. You tell it you want something to be executed at the exit of the program. So you say at exit, run the function do exit. And what we do in the final function before the program is exited, we report the maximum stack depth and how many function calls there were. And this is it. This is the entire CSI tool. So now let's take a look at the make file to build the tool and instrument the target program. If you want to have a look at I lost my mouse pointer. It's not good. Okay. The target program we want to instrument is a simple program that takes an argument and it takes an argument n and it returns to the power of n. To show off like stack depth and we implement 2 to the power of n as a recursive function in the worst way you can possibly implement this. Like this is a shift, but now we're doing recursive calls. So let's take a look at the make file. It's basically what I showed on the slides with actual, the actual thing you need is will be shared. So the 2 top things, the library for the tool and the bitcode for the tool. So the library you just compile as shared. The bitcode you can do -c -emit LLVM and you get the bitcode. Then you take the target program, in this case program.cpp, and you build this you say object file which is instrumented. So you say I want to use CSI, at CSI, I use this bitcode, so tool.bc, I compile with optimizations, and I just output the object file. And then the final step is to link everything together. I don't recommend to use LD like the linker. Instead use Lang as the driver because it will also link in for example, the C++ library automatically by default. Otherwise, LD sometimes you get like this symbol not found and so on because Lang does a lot of things in the background that LD doesn't. So I would say tool library, the instrumented object file, and the CSI runtime. Of course, you get that from the build of LLVM with Tapir that you will get from source. We also we have a target for the uninstrumented program, so to show like this is what you will do normally. So let's see how it goes. Where are we? Here. Let's make it bigger. So make does all it needs. Clean it. And then we just pull the instrumented binary as normal. But first, let's pull the uninstrumented binary. So let's do 2 to the power of 5. And just say 2 to the power of 5 32. Now we call the same, but with the instrumented binary. We actually have to because it needs to find the library and you need to tell it explicitly unless you do something else. This is the easiest way. So we see that it's actually being instrumented, and we get the final output. The maximum stack there was 7, and there were 8 function calls in total. Now, as I said, I have a verbose flag, so let's actually see. So we see here that for every entry or every exit of a function is instrumented, and we print whatever we want. In this case, we print the function name, and the current stack depth. So you can see it goes 2, 3, 4, 5 to 7, and then it starts going back. This is the stupid 2 to the power of 10 recursive mode. So this is how easy it is to build a tool that does arbitrary instrumentation. Now, as a bonus, I instrumented the code that I showed at the beginning, the obfuscated code, and let's see how it performs. So it still does the simulation of this constellation. This is not in verbose mode, so we get the output in the end, and it's up there. So it was pretty shallow, 6 of stack depth, but there were 110,000 function calls. And you probably wouldn't have guessed that by just looking at the source code. Go back for the final remarks. So some important considerations. The amount of instrumentation that you get from CSI depends on when CSI is run. The compiler is a long pipeline, and different optimization affect how much things you can instrument. For example, the default for CSI is to instrument at the end of the optimization pipeline. So you get, I would say, the least amount of memory access and inline functions and so on. You can tell CSI, I want to instrument the debug build of my program. So you will get a lot more memory access. You will never get an inline function most of the times, I would say, depending on the compiler. So it really depends. It's configurable. And this may be obvious to some, but some instrumentation is more expensive than other. For a general program, instrumenting every memory access is going to be more expensive than instrumenting every function call. Unless you have more function calls than memory access, then there's something probably that you want to modify for your program. As some hints that, like, if you want to get to know CSI, there are some things that I suggest to do. So this is almost in order of difficulty. You can start with an easy tool to count the number of calls to external libraries. You can then write a simple profiler, and that's the most expensive function in terms of time spent, or any metric you want, memory accesses. You can compute test code coverage. You have your test suite for your program. You want to know which code is never executed, so you want to add some tests for it. You want to write a tool that can detect out-of-bound accesses. So you can use the memory allocation functions instrumentation to first know which memory you're allocating, and then every time you store or load from a memory allocation, you want to know that this is not out of bound of any allocation you previously did. And then you can get more creative. You have some data structure. You want to find suboptimal memory access patterns. You want to improve your data structure by, for example, moving blocks of, for example, a hash table along or stuff like that. You can get very creative, and I suggest you just try and see what's possible to do with CSI. Yeah. So thank you. This is the source repository for the Tapir compiler with CSI and the original CSI paper, which you can find on that link. Thank you. If you have any questions. Yeah.
So as far as, can I filter which exact function?
Yeah, so I've actually done some work in that area. It's in, so you can provide a configuration file which says, for this instrumentation point, I only want to instrument these functions or these translation units. So if you want to say, I only care about main, so you can say instrument only main, or you can do this as a whitelist mode, so only main, only this function, only this, or in blacklist, say instrument everything but main, because maybe you don't care about main. So it is possible. Yeah. Yeah. Oh, definitely. Like, for example, if you run CSI before optimizations are run, it will, at the beginning, you have a lot of basic blocks because Clang will just produce as many as it can because it doesn't do any optimizations. So you can go from like 10 basic blocks to if you then run optimization, you could even reduce to one, depending, or just elide it completely. So it definitely changes, and you usually you want after optimization because that's what your program does in the real world, like in release mode. There are some cases in which I had to do at the debug stage because of like unexpected behavior that only occurred during debug builds. So, but yeah, it does change.
Classic example, that you arguably don't want to run after optimization, especially because even at the IR level, you imagine your conditional, and the conditional will conditionally perform assignment, for example. Without optimizations, that would turn into a standard diamond shape of basic blocks, but with some optimizations, you could say, I can do a conditional loop here, or select state into an IR. And now, when you extract your program, it says, yeah, I executed that state. But you have no idea whether you can actually exercise both paths, because
Yeah.
there aren't two paths.
Have you guys thought about using this tool with some binary instrumentation tools?
Yeah, so one big problem with CSI is that you can't instrument beyond the boundaries of your program that you're compiling. So, for example, if you're using external libraries, if you're doing like operations about memory, like collecting information about memory usage, you won't get to see the allocations done by an external library. In the image alignment case, it was a big problem because most allocations were done by OpenCV, which we didn't instrument. So in that case, so we kind of used some, I wouldn't call it binary instrumentation. We used we preloaded a special malloc and free. So it went through our malloc and free. We thought about integrating CSI with some binary instrumentation capabilities. The problem is it's unclear how well the two things are going to integrate. You want to disable binary instrumentation when in your code and enable it when you go above, like beyond the boundaries. We didn't do anything yet there, but it will be cool so that you can, and in an ideal scenario, you just write one tool that works for both. So, yeah. Yeah, so I've actually wrote a prototype of a JIT compiler that takes C or C++ code and JIT compiles it with CSI and is able to modify it at runtime. So that when you're running, you can, I would say in an interactive mode, you can say instrument this function, then run to that point with this instrumentation. Run it again with different instrumentation without like going out and like without restarting everything. So there is some cool stuff you can do with this. Yeah. Yep. Yeah, so We don't really do anything special there. We rely on the compiler. We know that adding instrumentation may make it impossible for the compiler to optimize code that otherwise will be optimized. For example, if you're instrumenting a memory access, that memory access will not be elided by the compiler anymore because you're doing something that relies on it. So there is a problem where, but I would say with any instrumentation, except for binary, is that you're modifying the code that you're instrumenting. So we don't do anything special. There may be clever tricks to do there, also for optimization purposes. We don't do anything special right now. It is a concern. Oh, that's so. I mean, I think for like testing purposes, you just rerun most optimizations, and then I done some work in that. I tried different optimizations to run after the CSI pass. Some really matter, like inlining, you really need to rerun, and some other like around constants. It's just as with most compiler stuff, it's heuristics and see how good it runs. We don't have a big body of testing for CSI though, so it may be definitely suboptimal with respect to the best you can get. And if we want to make sure it's optimized, we want to rerun as many as possible, and that's going to take time. Yeah. Yeah. And for next week, I don't think. Yeah, so there will be an email probably if there's. But in 2 weeks, I think.
In 2 weeks, we have